slide. Exactly. No need to. Okay, if you have any questions around here about the production, or somebody will not understand what it is, so please ask. Everybody knows what is a filament, yes? Yes?
In terms of the nonlinear coefficient for the atmosphere, what's the kind of, aside from laser issues, what color is best for easier making a filament?
Well, it is really hard to tell because at 800 we have a very powerful laser. At a little bit different sides, if you go to the green, so we lose some energy. So it is harder to find the laser which could be so powerful so as to initiate the...
But aside from the initial power, like what is the self-focusing, what color is best for the self-focusing in the atmosphere?
Well, I try to remember, there is a critical power which is written here. So this is the power needed for the beam to self-focus. And we see here the omega, or the frequency of our laser. So we see the frequency which is lower will increase the power, and the frequency which is higher will decrease the power. So it means that going to the infrared, to the ultraviolet, it will lower our critical power needed for the self-focusing. But it will be later. Okay, so this one, as I said, verify powers from here. You see some turbulence, and this turbulence can initiate into filamentation.
But this is irrespective of the power that you transmit.
Yes, as there more power, so it means that there can be more filaments appearing.
Okay.
And shooting from here, we do not have turbulence or reaction particles so much. So this is different species density, and in some cases we can have a fit of exponential decay, which is around 7 kilometers. I will need it because it is possible to write some analytical formulas. We have a propagation equation, which is this one. So here's the diffraction of our beam, and here's self-focusing of the beam, or the Kerr effect. If we will assume that the shape of our beam stays Gaussian, so here's the formula. We are searching for such a solution. We can simplify this one propagation equation into just finding the radius of our beam. So here's the equation which needs to be solved. And as I said, there is a critical power for self-focusing. So there is some threshold. If we reach this critical power, the beam will focus itself. If you do not reach this power, so the beam will defocus. So it does not have a nonlinear effect in the simplest means. If you will write that the nonlinear index or the Kerr effect depends on the height, which I wrote here, that's in this one, exponentially decaying, we can find the solution. It is quite complex, but still it is a solution. And as I said, it is a simplification, but it is we have a Gaussian beam, which is reshapes into just a Gaussian, and we have an exponential decay of our species, or the density.
This nonlinear effect in the atmosphere, it doesn't depend on the photon energy?
Well, it is
on the index of diffraction,
yes,
of course. But so because you said the longer the wavelength, the better. Is that what you said?
The longer the wavelength, this parameter will decrease, so it will increase this one.
So if the frequency increases, the power decreases.
Yes.
So less power is required for this effect. So the shorter the wavelength, the better.
Yes. Okay. So the next step was here's the same propagation equation, and here's the nonlinear refractive index, which can have not exponential decay, but maybe taken from the numerical simulations of the atmosphere, or what was called MSIS model. And we can use this data to plug it in and calculate the changes. We have developed the tool, numerical tool, which calculates this one, not assuming that it is just Gaussian and compresses to a Gaussian, so it is more broad, let's say. And calculating the critical length or the initial of the filament, we see that the results of moment formalism or the analytical equation depart from our numerical simulations. Well, it is not the best news. However, this analytical formula can show the tendencies. If, let's say, if you will change this parameter, how it will affect. Because to calculate the direct, numerically calculate such a collapse point, it is quite difficult. It needs time. And if it is just a formula, so it takes orders of magnitude less. Later on, we used only the direct numerical calculations. So there's critical high dependence on parameters. They're computed via numerical tools, not using analytical formula. Here I'm plotting the 10 kilometer height target. So let's say if we need to target 10 kilometers height, we want to analyze at that altitude, and we say, let's say, we have only 1.2 terawatt, I will need such a beam. And as I said, this one would be interesting area of the laser, so that we have a very broad band of altitudes.
So can you go back? So between 1.2 and 2.4 terawatts, also the yeah, of course, it's the radius of the beam. So
yes.
we need, of course, so it's the square of.
Okay, so this surface, the scaling law, can be fitted with some formulas, so as to easily just plug the numbers and get the result. So here are the formulas, and we see the fit is quite nice in all the points. Nevertheless, the formulas are quite nasty. But still we can plug our initial conditions, our beam radius and power, get instantly the result. Next I said if we will fix some radius and increase the power, we will increase the altitude of our initial filamentation stage. If we look at the individual radius, dependence on height, how does it change?
In your formula, do you take also the fact into account that the beam is converging, that it's focused?
Yes, yes.
Okay.
It comes from the
so it
diffraction.
means that the more power, the earlier this filamentation will start.
Yes, just because the nonlinearity will come.
Yes.
Okay, so if you look at the individual, here I'm plotting the blue curve as the linear case. I would also like you to have attention that it is in logarithmic scale radius and in logarithmic scale also the height. If we had only 10 peak criticals of the ground, so it will mean around 30 gigawatts, it does not have enough propagation to self-focus or to have a collapse before reaching the ground. Nevertheless, we see that nonlinearity acts. Later on, we will increase a little bit, so we see the collapse at 10 kilometers. And while increasing the power, we see that it is shifting to high altitudes. From the linear Gaussian optics, we see that if you put the lens, that the minimum of a beam does not correspond to what is written on the lens. On the lens, it is a focal distance. However, the minimum of a beam, in linear case, departs from it. We can calculate what what focal length we need of our lens to have linearly the minimum at some certain distance. In this case, 10 kilometers was the target, so I show the star. Fixing this lens, we see we will introduce again all these powers the same as here, and we see the same tendencies. It does not act a lot on our behavior of the beam. Here I'm plotting the height dependence on the ratio between the power versus critical power at that height. So this is 1. So it means that in this area the nonlinearity will take part as a major role. If I took red, so we'll go here and it starts the part at this height. If there is a dotted black, so it started the part a little bit further. Here I show that if we will fix some power and change the radiuses, our height has a tendency to vary, and we have a maximum at some point, and here a little bit more complicated. However,
can you go on to that just to understand this curve?
Yes, yes.
So you have a constant power, you have a...
Yes, and I'm increasing the radius of my initial beam.
Okay. You're changing the radius by focusing or by
No, the initial radius. So from the laser in the sky, in the satellite.
Okay.
Expanding it.
Okay. From the aperture diameter.
Yes, aperture.
Okay.
So as I said, here is a 21 centimeter width of our initial beam. If we will focus, we see it starts wants to focus a little bit, but due to diffraction it defocuses. So that's why the desired 10 kilometer length is not for the minimum of our beam. Here I took 21 centimeter beam, put it a lens, which corresponds a length of 390 kilometers. So if you focus from 400 kilometers, we are targeting 10 kilometers. What is the part? Okay, we have some power, we are propagating. Here our minimum of our beam, it is diffracting. However, nonlinearity takes part and focuses it.
It takes part because the atmosphere is getting bigger.
Yes, because it reaches the point where the nonlinearity, the ratio between the power and the critical power at that height is 1. It means that it focuses. So it starts to bend. If it will increase...
And why does it take so long? Why doesn't it start immediately?
Oh, because it like an accumulative effect. So it is very high intensity, so it's self-focus a little bit sharper. And if it is very broad, so intensity is very low, so it needs a little bit more longer propagation to the collapse. Here we increase the radius. We see the curve also. Here it is focusing and then collapsing, and with the red, which was the largest, we see that our focal distance and the minimum of our beam almost coincides to what we need at 10 kilometers, and this is the red. In some cases, we see that you can get the same collapse height with different beam radius, initial beam radiuses. And E now represents if we have a minimum of our beam at 10 kilometers for these three initial beam values. So we see that the tendencies are all there, and this part, which is depicted by the light blue, is nonlinear part of the propagation. So it means from this point the nonlinearity will take part. So in all the cases we see that it starts to depart from the linear propagation in that point. So state-of-the-art numerical simulations, what we did in a full and scale model, very complicated formulas. Okay. This is the unidirectional pulse propagation equation, which is written in this form. And here is an optical Kerr effect, which is including the Kerr self-focusing or self-focusing tendencies here. So now we account the current. So it means that current accounting different species. It means that while the beam compresses, it increases its intensity and can ionize the medium. Of course, medium is constructed with different species, so it can ionize different species then. So we have to have an account in this formula. Here's for the equations of the density of species. Here's our electron density, and of course this unidirectional pulse propagation also has the time domain, or can calculate also the radius and the pulse. Yeah. In some cases we can omit the pulse and just look how does the beam contract. As in this case, I used the 50 centimeter radius beam, and it was collapsing. And as I said, the beam contracts 5,000 times, so it is quite a lot for the numerics.
So if you see here is 400 kilometers, you have a 50 centimeter radius,
yes.
initial diameter.
Yes, initial diameter.
The beam is focused, it goes down, down,
Down.
Okay.
Here it is. Here our critical height.
Oh, it's a magnification of, okay.
Yes, right. So magnification, and finally we have.
And finally you reach enough energy density to start the process.
Yes, or the beam collapses. This one, and this is there is a plasma, so as I said, there was a current, so in current there is a plasma. These yellow spots.
Then can you go back? What makes it, I didn't fully understand. Okay, the beam collapses, nonlinear effect,
Yes.
but then it spreads again, but for some reason
It spreads because there is a plasma. If there would be no
the
plasma, so it
plasma
compresses,
is
and
this is the
infinite.
index of refraction that makes it
Yes.
going back. Okay.
It's different from the Kerr effect, so that's why it differs.
Do you expect any effect of the change of refractive index in function of the altitude? Because you create sort of a variable refractive index.
Yes, it's
10
included in
kilometers.
the code.
Then you have a grating basically, very, very low frequency grating, but still a regular structure, which might have
Okay.
impact.
It will be just points, so it is really hard to tell it is a grating. Yes, in some sense it is a grating of plasma.
Yeah, because I mean,
Points.
10 kilometers like in an optical fiber, because you are guided, and,
Yes.
through this length you have regularly refractive index change, which actually it would be a Bragg grating in a sense. Very low frequency, but
Well, yes, you mean just due to this generation of Bragg grading, you will have a
different behavior of the line. Maybe some wavelength would just be scattered back or something.
okay, I do not show, but also this plasma also absorbs energy. So in this case, the backscattered light is really, really low due to the laser. However, if you will propagate another, let's say, low intense beam, you will have a reflection. But it is already the second pulse after the first one.
Sorry, I think I missed your point.
Yeah, basically, I insinuate something, an effect, this person was very well, it's a Brunei effect. With an optical fibers, when you go, with CV beam, you know what Brunei effect?
No, I know what it is.
Yeah, but it's usually for a continuous wave.
Yeah. And this is
In
much
general,
less than
this is
nanosecond
pulse,
pulse
yeah.
duration, which is the time that it takes to generate the acoustic wave. So I don't think that it would play a big role.
Probably not, because it's so high frequency, or pulses, so,
Yeah.
The pulse is already gone in this plasma generator. You need
In
another
any
one.
case, the plasma density is relatively low. Is typically you can read it on the figure on the right is 10 to the 16 electron per centimeter. Even at this altitude, it's even lower. And for the, I think for the Brillon effect you referring to, it would mean fully ionized plasma in the sense the same density as neutral molecules. Or
No, to have a signal is just enough. Something at least. Okay. So we will compare 50 centimeter beam. Here's the initial one. And if we compare to the filament, so here's 100 micrometers. It's just 1 point or just a line, just because it is 5,000 times smaller. So we will have the same grid. Probably we will need 10 to the 5th numbers of points just to have an accurate result, which is ridiculously big. So what we did, we have here our initial beam, lower discretization, and after beam propagates a little bit, we see that the beam contracts 2 times, just due to the lens effector. But here, at the sides, there is basically zeros. What we did, so we added some numbers there, additional numbers, and removed these parts where the zero are there. Okay. Remove the parts where we do not have any information about the intensity, because we do not need it. And after the step, we will have smaller steps in space dimension at the same number of points. So we will save a lot of numbers, and we will be able to reproduce all the propagation effects. This just inclusion is not that simple, because we need the intensity fit, but also the phase, and the phase has jumps, and it is not that straightforward. We needed to go to the spectrum again and make some changes and go back again. So it was a know-how. So here I show the propagation of our beam. So here's the radial coordinate, and here's our time coordinate. Every slice is represented in the far field or the spectrum. So we said that here it is a wavelength, and here's our angles. It is a transverse wave vector, but still it can be translated to angles by such a formula. So here's angles, here we see the conical branches. At some point you see that the axis is jumping and it is reducing. So it means that our grid reduces by step function. It is shrink, so we can cut some point. Shrink, we cut some points. So we see it is compressing, and here we see even more compression. And after it, there is some dynamics. And in the spectrum, we see how does it populate. So it is almost like instantaneous.
Can you explain time? What do you mean?
Yeah, time
Isn't this
connected to a pulse.
Right?
It is connected to a pulse. So here at the beginning we had 500 femtoseconds. So our
Okay, so it's a pulse shape.
yes,
over
yes.
time.
So we are tracking the pulse.
Okay.
Then it is propagating through the atmosphere. And you see this, and we have available structure. Okay. Supercontinnum generation is associated to pulse splitting event. In this three figures I'm plotting. In the first one, it is the wavelength dependence on the height. So we have a collapse at 7.3 kilometers or so. And we see the very sharp and very broad spectrum generated at this point. If you look at here's the time coordinate, and here's the height again, we see that the pulse reshapes itself and generates one pulse and another pulse. So it was split into two. If you look at the fluence profile, here's our, again, the height or the altitude, and here's our R coordinate or space coordinate. You see it is contracting, the intensity is really, really high there, and when it is relaxing. So we see all these points are interconnected in supercontinnum generation, pulse splitting, and collapse. And again, we see these conical branches, and we can see that it generated very broad continuum, which is very good. And I said there are two very short pulses generated due to pulse splitting.
What is the percentage of energy that is absorbed or taken up by those nonlinear collapses? I mean, how many of these hotspots can you generate with them?
Well, everything depends on the material. First of all, at the beginning it is underdense, so there is no much power probably absorbed there. But when we go further, a little bit closer to the ground, there is more material or more atoms, molecules. Yeah, so there is also the Kerr effect. It also increases, so it also tends to squeeze itself. So it is kind of balanced. There is a need of more investigation there.
It's a few percent usually
Yes.
of the dimension.
Few percent.
At the quantum level at least.
It's not like 50 or
So you can have many. Usually the beam defocuses, the filament stops before the energy reservoir is exhausted.
Well, and then probably the last one, which is very tiny, 100 micron squared, will then create a huge divergence of the beam.
It's
Well, it is
not
also-
so large, it's actually less,
No,
it's
okay.
diverging less than it would diverge with linear propagation.
Really?
Yes,
Yeah.
just because of the conical branches. Where is my supercontinuum? So this makes almost like an X-ray non-diffracting on this perceivable. This interpretation of these conical waves and the X-rays can be read here in this publication.
Yeah, sure, but then here you converted the 800 nanometer light into a continuum.
Yes,
But the light that is still propagating is still 800 nanometers.
no, let's say the mass at the center of the mass at 800. It does not change in the center of mass very far. And here it is in logarithmic scale, so as you see, the supercontinuum is around 4. This. Okay.
But you can read angles from this figure actually.
Yes, here's angle.
0.2 degrees at 800 nanometers is the maximum.
There it is. And again, I show the supercontinuum and that it is broader than the Gomet-2 setup. And as I said, we have investigated different species ionization. So here's ion density dependence on the altitude. So we see at the beginning of propagation at 400, the oxygen was the most abundant. However, the oxygen molecule, O2, has a smaller band gap, so it is easier to ionize. And we see it is almost in all of the propagation, it is it contributes the most. If we will zoom in our collapse point, we see here's the oxygen ion density, and in the blue there is nitrogen. It has a higher band gap, so it is harder to ionize it. And here we see the argon, which is 3 or 4 orders of magnitude lower. So to simplify the simulations, it is possible just to take oxygen and nitrogen, and it will be much faster. Because at the beginning,
This is just for the ionization.
What?
Just for the ionization. You think
Yes.
that,
Due to this, how to account for plasma. So we can just use these oxygen and nitrogen molecules and save time a lot. And in perspective, we wrote that the control of a collapse via pre-chipping, so putting some phase modulation with our pulse will also vary the height of the collapse. Later on we could analyze the turbulence effect on the filament. How does it affect? However, we know that it will not affect a lot when the filament is formed already, because the turbulence scale is larger than our filament. But maybe in the initial propagation, it might happen that we need a turbulence account. Nevertheless, it is very under dense medium. So we could also investigate filamentation with different initial wavelengths, to put in the orbit different lasers, or maybe to shift our initial wavelengths to more infrared, so as to have more infrared expansion to analyze our particles in the air. It's possible to do three.
Sorry, but this would require then higher power levels. So
Yeah,
shift it
yes.
to infrared.
Yeah. Numerically, we can. We can make a 3D plus 1 simulations. However, it will require a supercomputer, because now we had a 12 core computer. We used only radius and time. It still take a week just to compute collapse. And we can reshape our beam maybe to super Gaussian or other profiles, just for fun, or maybe there is a better explanation. Maybe we have a super Gaussian and make a tube of intense plasma, and maybe we can transport energy or other applications.
We don't want to get too much diffraction until you reach this critical point, so you better stay with Gaussian, I presume.
No, for now it is just a Gaussian. Hover shapes are more tricky, so it was left for the future. So, of course, we can make lab-scale experiments as to show the density dependence on the filamentation. Like we can have a tank, put it water, let's say very high tank. So at the bottom it will be more dense than at the top of the tank. So we will have a change of density. And maybe just lidar and maybe ellipse laser-induced breakdown spectroscopy application analysis may be done. And conclusions the same as in the short talk. Thank you.